Today we're going to be talking about climbing stairs. This is what the problem looks like, and let me explain how it works. We're given an integer n as input. That integer n represents how many steps are in a staircase. And given that we can take steps 1 or 2 steps at a time, we're tasked with finding how many ways are there to get to the top. So as a simple example, so this is our staircase, this is the bottom where we start. To get to a staircase of height 1, we only have one option. We can take 1 or 2 steps, but because the height is only of 1, that's our only option. There's one way to get to step 1. What about step 2? Well, we can either take a step to step 1 and then a step to step 2, or invoke our 2-step jump and jump directly to step 2. So there's 2 ways to get there. How do we think about this generically, though? So I've drawn out the staircase to go up to n. That is our input after all. And instead, I want us to think in terms of variables where we don't know exactly what number we're on. Let's take step number n. So how do we get to step number n, or how many ways are there to get there? Again, the only ways we can take a step are with a step of 1. In this case, that would have to come from step n minus 1. Or we would have to take a step of size 2, which means we had to have come from step n minus 2. Conveniently enough, because those are the only 2 possible actions we could take, that means that these actions that we've just drawn out represent all possible ways you could get to step n. You could say we haven't solved for that yet, but what we can write, or what we can conclude from this, is that the number of steps it takes to get to step n is equal to the number of steps it takes to get to step n minus 1 plus the number of steps it takes to get to step n minus 2. So we've come up with a recursive formula for this, meaning that we have in a sense solved the problem. We just have to do this for every single step all the way down. But you might realize that doing this from top down, from n down to 1, is a little problematic because s of n minus 1 breaks down into s of n minus 2 plus s of n minus 3. Similarly, s of n minus 2 breaks down into s of n minus 3 plus s of n minus 4. This branches really quickly into an exponential problem, which is generally pretty bad for any computer science program. What we can do to mitigate this and make this a lot better is to work from the ground up. And if this isn't obvious why this works, it's actually a common concept in computer science called dynamic programming, and you'll see how it works in this problem and hopefully see it again and learn it in the future as well. Okay, so let's get to actually coding this out. So like I mentioned, we're going to build our solution set from the bottom up, so from step 1 all the way up to step n. And to help us do that, I'm going to have an array of length n representing how many times or how many steps it takes to get to each step. So the first box or the first item in this list will represent how many ways there are to get to step 1. The second item in this list will be how many ways to get to step 2, etc. And because we're building bottom up, unlike in recursion, we need to start off with our base cases instead of end with our base cases. So that's where I'm going to start. Our recursion goes 2 layers deep, so we're going to do 2 base cases. If n equals 1, like we talked about earlier, there's one way to get to that step. And if n equals 2, then we're going to return 2. Now for the building up / dynamic programming part, we will do steps 0, meaning the first item is 1, and the second item is 2, representing how many ways there are to get to step 1 and step 2 respectively. Now we do the actual building part. So for I in range 2, starting at step 3, all the way up till n, our last step, we're going to perform our recursion, but backwards. So steps I equals steps I minus 1 plus steps I minus 2. And this will loop through, go all the way to the end, hit the top step, calculate that, and that last item is what we want. So we'll return steps of -1 representing the last item in that list. We submit this, and we're golden. So what's the runtime? The runtime is just O of n. We're doing a bunch of constant time operations here. And then this loop is where we do the meat of the work, building up the entire staircase. And in each iteration of the loop, we do a constant time math operation. Finally, we return it, again, a constant operation. So our overall runtime is O of n. And one more thing to note is that in this particular solution, I did steps equals this array of length n, meaning that we used O of n space. I didn't think that was a big deal. Usually space complexity doesn't matter as much in these problems, but you can relatively straightforwardly make this an O of 1 constant space. Cool, that's it.